the test for the ambiguous cases for the law of sines. As you've learned, the law of sines can be used to solve for any triangle when you know the measure of an angle, the length of the side across from that angle, and either one other side or one other angle. Most textbooks state the law of sines as the length of side A over sine of angle A equals the length of side B over sine of angle B equals the length of side C over sine of angle C. Now, as long as you know two angles and one side, using the law of sines is no problem. You'll always get just one triangle. But if you're given two sides and one angle that's across from one of those two sides, we can run into some problems using the law of sines. Because it might be that there's no triangle possible. We may get lucky and there's one triangle possible. Or we could even have two different triangles given the information. So how do you know which is which and what to do when? Well, that's what this video is all about. There are two cases that we have to deal with, and I'll deal with the most complicated one first, and that's when the given angle is an acute angle. In this situation, we've been given an acute angle, and notice that the side opposite that acute angle is shorter than the side adjacent to the acute angle. In the diagram, the third side is somewhere along the baseline that goes across the screen. Now, if you look carefully, you'll notice that there's a circle centered at angle 2, whose radius is the length of the opposite side of our triangle. It's also tangent to the baseline. So if we were to measure the angle at angle 3, its measure is 90 degrees. That means that our triangle is a right triangle, and our right triangle trigonometry will work to finish solving this triangle. Remember that the definition of sine of any angle on a right triangle is the side opposite that angle over the hypotenuse. Now, in our diagram, the hypotenuse has been labeled the adjacent side, so don't get confused on that. But if we take that proportion and we solve it for the side opposite that angle, we'll see that the hypotenuse times the sine of our angle is equal to the side opposite our angle. So in our picture, if the adjacent side multiplied by sine of our given angle is equal to the opposite side, then a right triangle is formed. Now, in all of our cases, when we have an acute angle and our opposite side is shorter than our adjacent side, we're going to be comparing the opposite side to this product of the adjacent side and the given angle. In this situation, we'll have exactly one triangle, and that triangle is a right triangle. This time, we have an acute angle. Our opposite side again is shorter than our adjacent side, and again I have a circle drawn centered at angle 2, whose radius is the length of the opposite side, and notice that no matter how I rotate that opposite side, it never intersects that base side to give us a complete triangle. Now, from the previous problem, we know that we need to do a comparison of the length of the adjacent side times sine of the given angle, and here that's 4.05. Now, if I compare that to the length of the opposite side, you'll notice that it's larger than the length of the opposite side. So if the opposite side is smaller than the adjacent side times sine of the given angle, then there's no triangle possible. This diagram represents what happens in the third and most difficult part of the law of sines. Here, again, we have an acute angle, and our opposite side is shorter than our adjacent side. And if you look carefully at the circle that I have imposed on the diagram, you'll notice that it intersects the baseline in two different places. One of those places, right here, creates one triangle, But I can swing around the circle and I have yet a second different triangle formed here at the second intersection of the circle and the baseline. Now, from our previous work, we know we need to do a comparison of that adjacent side multiplied by the sine of our given angle, and we need to compare that to our opposite side. So that adjacent side times sine of our given angle here is 4.02. Notice that our opposite side is bigger than this product. So this time, if the opposite side is larger than the adjacent side times sine of the given angle, there are two different triangles. In these three examples, we've specified that the given angle has to be acute, less than 90 degrees. The side opposite that angle has to be smaller than the side adjacent to that angle. Now, what happens if the side opposite our given angle is larger than the adjacent side? Well, in this diagram, I have an acute angle as the given angle, and the opposite side is larger than the adjacent side. And I have exactly one triangle possible. Now, I agree. I could take this side and I could rotate along the circle until it comes over and touches that baseline at this point and create a second triangle. Problem with that is that this given angle is no longer the 44.07 degree angle that was specified in the problem. It's the supplement for that angle. So there's only one angle possible in this diagram. So if the opposite side is larger than the adjacent side, then there is exactly one triangle. The same thing happens if the given angle is greater than 90 degrees. If the opposite side is bigger than the adjacent side, then there's exactly one triangle. Although I could swing angle 3 around to the other side and create a triangle, the given angle is now the supplement of the angle that was given in the problem and not the 109.08 that we were told to use in this problem. So, if the opposite side is larger than the adjacent side, then there's only one triangle possible if your given angle is either acute or obtuse. The last thing we need to check is what happens when we're given an angle larger than 90 degrees and the side opposite that angle is shorter than the side adjacent to that angle. In our diagram here, notice that although the circle does intersect that baseline, it does not intersect the baseline on the side that we need to have it intersect on to have the obtuse angle. So if the side opposite the given angle is shorter than the side adjacent to the given angle, then there is no triangle possible. Wrapping the ambiguous cases for the law of sines up, if our given angle is smaller than 90 degrees and the side opposite that angle is shorter than the side adjacent to that angle, then there are no triangles possible if that opposite side is less than the adjacent side multiplied by the sine of the given angle. There's one right triangle if the opposite side equals the adjacent side multiplied by the sine of the given angle. And there are two different triangles possible if the opposite side is bigger than the adjacent side multiplied by the sine of the given angle. Now, if our opposite side is bigger than the adjacent side, regardless of what the angle measure is, there's exactly one triangle. And if we have an angle greater than 90 degrees and the opposite side is smaller than the adjacent side, then there are no triangles possible. I hope this helps you in determining how many triangles are possible in the ambiguous cases for the law of sines.